I grew up in a small town in Skåne where I went to school for 9 years. My mentor, that was also taught math, was one of my favorite teachers, and I told her that I wanted to apply for natural sciences in high school when I was ending junior high. She gave me this astonished look and said, "Wow, that's difficult, right? But I'm sure you can do it." I was 15, not very concerned, and I walked away from the situation. The next year, I was in high school studying math, biology, and physics. After graduation, I applied for university and started at industrial engineering in Lund. I was actually more interested in continuing on the science track, but I had heard from a lot of close friends and relatives that engineering and physics would be difficult, and I started doubting whether I was able to do it. 1 year later, I ended up changing my major to physics because I missed being astonished with the wonders of the physical world, and I was not really ready to give up learning about it. When I changed program, it was becoming evident that people in my surroundings, some that were even studying the same thing, were under the impression that engineering should be difficult. So I started changing the way I spoke about my education, always trying to wrap it in little sweet packages just to keep them from getting uncomfortable. If you study engineering at LTH, Axis has always been on the horizon as a potential employer, with innovative employees and opportunities to test a lot of new and cool technology. I applied for a personal meeting during a work fair and got to meet with a very down-to-earth man that had been working here for a lot of years. The entire meeting was very relaxed, and we spoke about technology and our interests in general, and it led to me getting a job interview. However, my first thought when I was going for the interview was that I had no idea what I was doing. How could I, had only been programming for 3 years, contribute with something to a well-established company like Axis? Let alone compete with boys that have spent their entire youth in front of a computer. Programming was difficult. I'm not trying to say that everyone had the same experience, or even that I didn't have support when I grew up. My family always supported me and stood by my decision, but it was a constant pace that I was doing something hard that eventually got under my skin and made me think that I was not able to do these presumably difficult tasks. Or even worse, I didn't want to. There are few people, even less girls, that connect comments like, "That sounds difficult to you. You sure you want to do it?" Slide off. It's a constant stream of opinion targeting us at a very early age. And if any of us here today had listened more than we had ignored, we would probably not be where we are. Because what is scarier than heading into a profession that is labeled difficult? Well, at least I think that it's heading into a profession that's being labeled difficult, while at the same time being a minority. According to the Center of Statistics in Sweden, SCB, only about every fifth developer in Sweden is female. I mean, every fifth. That's not a lot of people. And that's why I'm here today. And I hope that's why you are here today. Because my hope for this lecture is to inspire you to apply for jobs within programming and to even out these still silly, depressing statistics. My name is ElinOlofsson, and I work as an embedded software engineer at Axis Communications in Lund. I want to talk to you about what it's like to work as a developer and give examples from my life about what one can work with. In the end, I hope that working with programming will feel less intimidating and a lot more exciting. When I applied for the job at Axis, they were looking for an embedded software engineer with machine learning experience, and the most recurring word in the work description was analytics. Analytics was about as cryptic to me as the phrase AI, a term that I have come to resent over the past few years due to its exaggerated status in media. I mean, come on, if the only thing I would have to do for a couple of weeks was learn how to recognize 100 different birds, I wouldn't have been called groundbreaking, more like categorically obsessed. Joke aside, to quote Wikipedia, yes, that's allowed when you're an adult. Analytics is a discipline within computer science and information systems to discover patterns in large amounts of data. More specifically, in my team, we work with developing algorithms that find information in video that would be relevant for an operator. For example, someone might have walked into a restricted area, or that they drove past 10 cars on a small car path leading up to private property in the last hour. Or maybe that the same person had been walking around doing suspicious things in a store for several hours. One of the most exciting things about working in a team targeting analytics is that the project assignments vary a lot. They range between reading freshly published articles about new algorithms to implementing features in an application. That means that we have the opportunity to get inspiration from current projects that launch real solutions to real customers, while some of our projects are highly experimental and might not be executed fully until a few years from now, if ever. Being a back-end developer that is focused on machine learning also means I encounter a lot of different programming languages depending on the current project. For deep learning applications, the leading frameworks today are TensorFlow or PyTorch, both implemented in Python and open sourced. Thanks to a large community that's interested in deep learning, it's very easy today to set up a new test environment for a new or updated algorithm and have your first results within a few hours. Given, of course, that everything is bug-free, which is not to be taken granted, as you probably know. Most of our projects often start out in Python, but we test the wanted functionality or train a deep learning model to be better at, I don't know, detecting cars, for example. If the concept proves efficient and we want to deploy an application based on new technology, we rewrite the code in a not so high level language like C or C++. Programming in C for the first time might be intimidating since you don't have as many airbags as higher level languages. For example, you know that you have to keep track of memory dedication and removal of the same memory. But like any other language, writing C code is just another way of expressing yourself. You wouldn't be comfortable speaking Swahili the first time you came to Kenya, but the best way to learn is to try to make yourself understandable and use the new language as often as possible. One of my biggest fears, sorry about that. One of my biggest fears about taking this job was that it was going to be difficult and that the experience level that was expected was way above one I could provide, especially over a large range of languages. The truth is, just a week or so after I started, I realized that my fears were completely misplaced. Nobody knew everything, not even people that have been working as software developers for a long time. When I asked for help from a lot of my most senior colleagues, it wasn't unusual that they opened a browser and searched for something on Google. And that's the absolute best part by using open standards for programming in. My pre-existing expertise in language was seldom the limiting factor to whether or not I could program something. Rather, it was my ability to find the relative information, either from documentations or by talking to my colleagues and learning from code reviews. The biggest difference between me and my coworkers was that they weren't scared to admit that they didn't know something. They used the infinite resources of the internet the way they're supposed to be used, as a means to support everyday work. This is something that I would have loved to hear 6 years ago when I started university and way before my first encounter with programming. Or even 10 years ago when I was heading into high school, this would have been a valuable input from work life. To have a certain level of expertise in a certain area often means that you don't have that in-depth knowledge about something else. But the day you need it, you can always trust Google. Another aspect that I want to talk about regarding programming at a company comparison to working for yourself or in a school project is the perspective you have of the code. In my team, we work with relatively small parts of the firmware that is run on our cameras. In reality, this means that the overview that one has over the entirety of the code base is pretty non-existent if you haven't been working with it for a really long time. It's usually not the same teams that take care of front-end and back-end parts of the code. Working on your own project gives you the flexibility to control every aspect of the code and the program. You have full artistic freedom, but when you work as a part of a much larger firmware team, your focus is often much more controlled by detail. Functionality should be exactly as expected where it's expected, and the code style should fit in with the rest of the code to make it readable. One of the most important tools that we use on a daily basis, I would say, is Git. I cannot stress the importance of using versioning programs enough, especially when you work in larger developing teams. When I started working here, I had maybe made one push to a Git repository ever in my life. It was very new, and it can be very scary with the new tools. I mean, let me tell you, Git conflicts could be a dark and messy place. But the more I've worked with Git, the more I've realized how valuable it is. I'm not sure how comfortable you all are with Git, but I want to say this anyway because I feel that it's that important. So, Git is a tool to help you keep track of your entire code history, and you can use it to go back to the future. Oh, sorry, go back in time. If there are more than one developer working on the same code, Git helps you with showing where you both made changes so that you can combine the two solutions in the best way possible. It also lets you review each other's code to make sure that you agree on a functionality before it's pushed into the main code repository. Honestly, it takes a little while getting used to before you appreciate all the advantages, since it can be quite a hassle to go through and fix merge conflicts. My tip is therefore to learn by playing games. It's easier to remember what you learned when you had fun figuring it out. So I want you to really say this properly. So there's nothing else that you should take with you from this lecture, then please learn Git. I promise you it'll be worth it. So I'm gonna ask you to do a little exercise with me. All right, pull up your hands like this. We're gonna do finger stretching. And at the same time, we're gonna sing a Git song. Okay, left finger up, and then down and out, out. And then we do the same thing with the right hand. And then we say G, I, T, Git, use, Git, use, Git. Okay, you got it? Perfect, because I'm going to remind you, Git is important. Yeah, okay, done. In the beginning, I promised that I would show some real life experience or examples of what we work with here at Axis in my team. We develop backend technologies for some of our applications that are used in cameras today. And that's why it's so important for us to stay close to the researching field to make sure that we understand what technology might be interested in a year from now so that we can start looking into implementations early on and be in the forefront when it comes to technology. Our main focuses today are motion detection and different types of object detection. And quite literally, no technology is too big or too small. We have everything ranging from very generic models that has to be applicable in all types of situations in all over the world. And we also have very specific use cases where you can assume certain things about the setup that are always true, which makes the model, the application quite more, doesn't have to be that specific. On one side, we supply algorithms that are very general, and they should function wherever the camera is positioned, whether that be in a parking house, in a major city, or overlooking a poorly lit dirt road leading up to a construction site. And such an algorithm must uphold certain standards. We must make sure that we can rely on it in every single situation. And it also must run at a reasonable frame rate so that there aren't large holes in time where we don't know what's happening. Updating this algorithm is a continuous work, and as we learn about newer corner cases, we want to keep iterating how the model functions. One of the application packages that can be got bought with an Axis camera today is called Guard Suite. It's used as a way to help camera operators study a scene and make sure that you have an extra protection to find if people are trespassing or cars are trespassing. For example, a part of this application is called Fence Guard. As we can see here on the screen, an operator can draw out a virtual fence and make sure that an alarm triggers whenever a person or a car crosses that line. It's also interesting that we can set up what direction it's okay for our persons or cars to pass the line. So we want to make sure that no one can walk onto the site, but it's okay for employees that have been working there to walk out. So what happens is that the application recognizes that there's a person that's moving around, and it's okay for that person to walk on the road that's on the outside. But as soon as this person walks across the virtual fence, we can see that the line turns red and the application has triggered an alarm for an operator. behind this application, there is an object detector running that detects these particular objects of interest. For example, these are cars and people, person. And this detection model is one of the things that are developed and supported by our team. On the other end of the spectrum are algorithms that are much more specific and only meant to function under certain constraints. Maybe it's okay for them to take a bit longer during processing time, or maybe we know that they will always be used during daylight hours. We've had a summer work going on right now that have been looking at the possibility of triggering an alarm whenever someone places something in front of an emergency door. And this is to help operators and stores keep that extra safety and to make sure that they don't place anything in front of an emergency exit. And for this particular use case, we have quite strict constraints. We know that the camera is going to be placed overlooking a door and it's going to be inside. When the application is running, it's most likely also that the store will be open, meaning that the lights will be turned on. The scene is also going to look quite similar no matter where the door is placed. So even if they might have different colors, they overall have this kind of same shape of a rectangle, and it's most of the time placed on a door. This type of algorithm doesn't have to be as generic, and the corner cases are a lot fewer, leading to the algorithm often having a lower complexity than a more general model. And that's the fun thing. We support all these types of different use cases where we look at very generic situations that's supposed to be solvable throughout over the world in different situations, while at the same time targeting these very specific use cases that basically look alike all the time. So what you just saw is a demo of me and one of my coworkers. We're walking around in the office building, behaving like lunatics, to test out whether or not an algorithm can identify us as human, even though we don't look like most humans do when they walk down the streets. There were a couple of different algorithms running, but mostly they were based on segmentation, with the exception of a key pose estimator. Segmentation is quite interesting, actually, and I thought I'd talk a bit more about that with you today. Segmentation algorithms have just recently extended the family of object detection and have increased the amount of information that's given from a frame. So my idea is that I introduce segmentation, and then we go through like the workflow that we use to end up with a back technology for an application. So we start out at an idea with a concept, and then we test it out, we go forward, and we finally deploy it on a camera. All right, it won't be so very technical, but we'll see. So there are three main types of segmentation algorithms. The first one is called semantic segmentation. Here, when we use this type of method, we're mostly interested in looking into the background data of an image. So if we look at the example, we see that we can identify that there are cats in the image. They have a particularly class color. We have some sort of background, and we see that they're sitting on something else. There is no more information about how many cats there are or where they're located. If you want to use, or if you want to get that type of information instead, you should upgrade your model to an instance segmentation one. So this is essentially a more fine granular way of doing object detection. So in comparison, we see here that we have a few red boxes. And these can be seen as the bounding boxes that a standard object detection model outputs. But when we get this instance segmentation, we get the identity of all different cats in the image, as well as their exact location, meaning that we know more where the cats are, and based on the look at the segmentation maps, we can estimate their pose or what they're doing. So it gives us more information. Finally, we have the panoptic segmentation model. And this can be seen as a combination of the two previous. So it has introduced two new terms that's called stuff and things. And this is to differ between like background classes and classes that we're interested in instances of. So stuff is basically background. That's what we talk about when we say, there is a sky in this picture, or there are buildings, or there is a door at the end of the hallway, or a couple of windows on the wall of the building. We're not really interested in knowing where these stuff are, how many there are of there. I mean, the sky is still a sky. And they're just there to make our background information more dense. When we talk about things, that's the type of objects that we're interested in knowing how many and where they're located in the image. So the things in this image are the cats. And we see, similar to the instance segmentation, that we have the segmentation maps of the different cats, and we have identified them as individuals instead of a group. We'll take the semantic segmentation example as an example of how we can start building our application, or background technology for an application. So a semantic segmentation model might be interesting for us to help us understand what types of scenes our camera is located at. I stated previously that an Axis surveillance camera can be placed at any different location in the world. Like knowing if you're located inside of a parking lot or outside overlooking a garden might be vital for understanding how you should detect objects in the best way. And that's why a semantic segmentation model might be very interesting. This means that we can understand the background, so we can see what the image actually sees, or the camera actually sees. The semantic segmentation model works like this. We have the input image, and we get this segmentation map. And as we can see, similar to the previous image, we don't really differ between the person and the bicycle, because they're not really interesting. What's interesting here is to know that on the top of the image, we have trees. It's lined with grass in the bottom. And then finally, on the inside, we have a pavement or a dirt road or something in between. And that's what's important for us to understand if we set up a camera at a new location. So now we have the concept. We understand why we want to use the semantic segmentation model. So we'll just go through the steps that we would do if we were to set up this application. A general workflow goes as this. This model was predefined or pre-trained and located at the TensorFlow GitHub main repository. It's based on the DeepLab v3, and if you want to, you can go into this repository, find the model yourself, and then run inference on it to see how it performs. Since pre-trained classes and pre-trained models might not have the focus that we're interested in for our camera applications, we need to create our own data sets and train the model in a way that makes sure that we target the correct image types. So we use the TensorFlow repository to set up a training pipeline. We tweak it and peak it depending on how we want to specify our model. And then finally, we get something that can help us on the scenes that are specific for our cameras. When we're done with that, we're going to export a T-flight graph. And T-flight is a format that's basically just TensorFlow, but downsized into a smaller dimension. So we scale off a lot of unnecessary classes, but we still keep the same. We still keep the important layers that are normally used in a deep learning model, like convolutional layers, max pooling layers, or activation functions. And T-flight will help us to deploy this model on different types of hardware. All right, so now we've retrained our model. We made sure that we have it in a format that we can use on basically any hardware because it's so downscaled. And then we want to start thinking about how do we want our application to work? What is it we want to do with it? And that's where we create our context. And this is often written in C or C++, but for this example, we're writing in C++. So first, we want to fetch an image from the camera stream. We want to perform an inference on it and make sure that we get the results from the segmentation model and output it back to the camera. Here we want to create an overlay. So more or less just a color map of the different classes that we have and put it on top of the original image. So we can see where the different classes are in relation to the actual image, to the actual input. Finally, we deploy the model in context on the camera, and then we can run it, see what types of backgrounds and context that we have in our different locations. That was just a very small example, and there are obviously a lot more to it, but I hope that you understand the idea that we go from something very, very simple, from a concept that we look into. And then when we find our use case that we can use this concept for, then we start diving deeper and deeper into our own specific territory, where we look at use cases and situations that are specific for us at Axis, and then create context that we can use on our products. All right, so I know the session isn't interactive, and I pre-recorded this like a week ahead, but I'm going to try to do this anyway. So I want you to think about how deep learning can be used in combination with game development to create something new and really cool. I know you looked into creating games with React.js here during the camp, and I hope that you have like some new tickling ideas about what types of games you can create using machine learning and using machine learning basically. So I would love for you to take a few minutes to think about, just to brainstorm, write down questions if you have them, And I will be really happy if you would send an email to me with any suggestions or ideas or concerns. Elin.Olofsson@axis.com. All right, I'll give you 2 more minutes now, and then I'll talk to you later. As with any new job or social context, one of the first things we struggle with is to find our place in a group. Unless you're one of those weirdly extrovert people that are completely comfortable around new people, which I am not. This can be especially intimidating if you know that you don't fit into the demographics of the group. Like I said earlier, the demographic distribution in most tech companies are not particularly versatile. I even had a coworker that said, yeah, it was one of the men in the team. I can't really tell them apart because they all look the same and dress the same when asked to describe the person who had made the delivery. In my first project, I was part of a 4-man team that was in charge of evaluating offers from external vendors. We had a lot of cross dependencies with other departments within Axis and often had meetings with these groups to discuss how the solution could fit into all of our descriptions. During the first couple of meetings, I felt how the attention of the room slightly ever so shifted onto me whenever I walked in with my colleagues. There was never any hostility, but the extra attention made me lose some of my comfort, and during certain days, it made me sit back and try not to stand out in the group. Sometime into this project, I realized instead of trying to blend in, I could use the fact that I was already standing out. People were already seeing me, not always for the right reasons, but I could use their attention to ask questions, to put forward suggestions, and make business relations, to make myself heard. As a person, I have grown immensely the last year, partly because I have been given the opportunities to test and explore interesting subjects to me, but also because I've learned to trust my instincts. My instincts that tell me if I want to do something or not. And I have started to ignore anyone in my surrounding that tells me that something's going to be difficult. That programming is only something for the computer-loving boys that now have grown into men. Difficult has rather become a trigger word for me, and I could probably jump off a cliff to prove to someone that it wasn't that hard after all. Probably not one of my best traits. I do not recommend jumping off cliffs. That's extremely dangerous. But my point is that when you have a profound interest in something, whether it's math, programming, or even jumping off cliffs, doing it is not difficult at all. On the contrary, it's so easy. It's so easy to do something that you want to do. It's easy to learn something that you want to learn. And most of all, it's easy to do something when you have fun. Please think of the funniest thing that you like to do and tell me that it's not easy to take your time to do it. Programming. Okay, what was that? Programming is easy. I hope you took something with you from this lecture. At the very least, that Git is important, remember? And even though this isn't an interactive session, I would love to hear your thoughts and experience around what I've been talking about. If you might disagree completely that programming is considered a difficult job. So please write down your questions and send an email to me. My email address is, like I said before, elin.olofsson@axis.com. I'll show a few videos now to just give you a few minutes to think about what you wanna ask or what you wanna take away with you from this lecture. So enjoy.